Hello, Algebra 1 honors. Oh, I said it again. Hey, Algebra 1, how's it going? Today we're looking at lesson 2.1, and it's introducing us to functions. And these notes are kind of long. There's a lot of interesting things about functions. So you can see our objectives there. There's 4 of them. And we're going to start out by determining whether relations are functions. And to say what needs to exist for any relation. Oh, by the way, a relation is a pair, inputs paired with outputs. You see this a lot in the world that we live in. You know, you might have the day, and then for the day you have high temperatures. So the input would be like the day of the week, and then the output would be the high temperatures. But we often pair data together, and those are called relations. But if a relation has exactly one output for each input, then what you can do is you can call them a function. Okay, so that's what we're going to focus on today. Before we get there, though, this data, this printed out funny. It's supposed to be over here with B, so let's fix that first. Google Chrome kind of stinks a little bit when you try to save math stuff in it. It doesn't always get the spacing right, and so it kind of messes things up. But anyway, so example 1 says determine whether the relations are functions. And so I want you to keep in mind that when you're given an ordered pair like this, you've got an input paired with an input of X and output of Y. And we want to check to see if each input has exactly one output. Well, sometimes it's hard to see when they're written as points like this, but I'm noticing -2 goes to 2, -1 goes to 2, 0 goes to 2. So that's weird that they all go to 2. But each input so far has one output, so we're in good shape. And then 1 goes to 0, 2 goes to 0. And again, kind of strange that those both go to 0, but each input seemingly has one output. Now, to double check, it turns out that relations can be written a lot of different ways. One way to really be certain whether or not it's a function is to make a mapping diagram. And what it is you're going to have an oval for your input, an oval for your output. And for your mapping diagram to tell you whether or not somebody's a function, you want to write everything that shows up in the input once, everything that shows up in the output once, and then it'll tell you if your input has more than one output. So for our input, we've got -2, -1, 0, 1, and 2. And we didn't have it repeated at all. For our outputs, we've got 2, but it's repeated. We got 2 again, 2 again. We're not going to write it more than once. And then we got 0 repeated as well. And then to complete a mapping diagram, you draw arrows. An input of -2 had an output of 2. An input of -1 had an output of 2. An input of 0 had an output of 2. But notice each input only has one arrow coming off of it so far, so we are in good shape. So far, this is a function. We just got to finish the data. 1 goes to 0 and 2 goes to 0. So this is in fact a function. This is a function. Each input has exactly one output. It was weird that a lot of those inputs went to the same output, but that's okay. As long as there's only one output for each input, we're good. So let's look at this next set of data. I'm seeing an issue already, okay? I'm seeing that 4 goes to 0, but later on 4 goes to 3. So that's going to be a problem because an input of 4 shouldn't have 2 outputs, but it does in this data. And to really drive home that point, let's draw our mapping diagram. We've got 4, 8, 6, 4 again. We don't write it again. we've already written it. And then 5. And then on the outputs, 0, 7, 4, 3, 2. And what you're going to notice is 4 goes to 0, 8 goes to 7, 6 goes to 4, but then we have 4 going to 3, and we could stop right there. It's not a function. This input has 2 outputs, so that's a problem. But we also have 5 going to 2. So whenever you find out that something's not a function, you should be able to like circle it. You should be able to circle the input that has more than one output. Excuse me. So yeah, is this a function? No, it is not. 4 has 2 outputs. That's an issue. And then you can also have relations displayed as tables, like so. This table is kind of spread out horizontally, like that. And again, I'm seeing an issue here because we got the 0 going to 5, and later it goes to 6. So one input of 0 has 2 outputs. So I already know this is not a function. No, 0 has 2 outputs. But you could also write this as a mapping diagram. And so I just want to make sure you guys are really good with these mapping diagrams because it's a good way to check. So our inputs are -2, -1, 0, repeated twice, but you don't write it twice. You just write it once. 1 and 2. And then for outputs, we've got 3, 4, 5, 6, 7, 8. All right, so -2 goes to 3. -1 goes to 4. So far, so good. 0 goes to 5. 0 goes to 6. Oh, yep, 0 is the problem. 2 outputs for 1 input. The machine is broken. This is not a function. 1 went to 7. 2 goes to 7. So, yep. Also, you know, just another little example here. Again, it's okay if multiple inputs go to the same output. And so to drive that home, take a look at this one. 1 goes to 5, 2 goes to 5, 3 goes to 5. This is a function. Each input goes to exactly 1 output. It just so happens the output's the same for all of them, but each input goes to 1 output, so this is a function. Yes, it is. All right, so yes, it's a function. All right, you can also represent relations with graphs. If you've got x's and y's, you've got coordinates, you can graph points, you can graph shapes. You can put all those points together to make shapes. And there's a shortcut you can do if you've got a graph of a relation to tell if it's a function or not. And it's called the vertical line test. And so what you do is you scan the graph with a vertical line and see if it only hits the graph once. So remember, these x's are inputs. And so as the x is going along, see how many y values it has. And if it only hits the graph once, that means each input has exactly 1 output. So yeah, this is totally a function. And I also think of it as like radar. Beep, 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 beep. Nothing on the radar, it's good. But if you check out this is actually, if you were to graph y equals plus or minus square root of x, that's roughly what this graph would look like. But you see here, each input does not have 1 output. It fails the vertical line test. Beep, 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 rant, 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 rant. The vertical line test fails because this input of, let's say it's 4, has 2 outputs of 10 and -8. That's an issue, not a function. This one, this is an ellipse, not a function. This input of 5 had multiple outputs at 6 and -6. So that's an issue. Fails the vertical line test, not a function. So think of it as like scanning the graph. Well, let's see what else we got going on here. Oh yeah, try it out. Ooh, you'll find out this is called discrete data when there's spaces in between. But yeah, determine whether it represents a function. It fails the vertical line test right there. Fails vertical line test, so no. Fails vertical line test. Or you could be more specific. You could say no, 2 has 2 outputs. 2 has outputs of 2 and 5, and so you could say it that way. And then for that ray right there, you'll learn more about rays in geometry. You would say, does it pass the vertical line test? Yeah, it does. It passes the vertical line test. We're good. So is this a function? Yes. And you can simply say passes vertical line test. Cool. All right, so now we're going to talk about domain and range, and we're going to actually take tomorrow to practice domain and range the whole hour, okay? So we'll practice this some more. But domain is the set of all possible input values, and the range is the set of all possible output values. So you guys watched a video about function introductions, and they talked about sets and how you write those and things like that. So let's go ahead and dive into some examples here. Find the domain and range of the function represented by the graph. So they already told us it's a function, so it passes the vertical line test. That's cool. But they want us to write domain and range. Domain and range for the graph. Well, the domain is the set of all the input values, and our input values are the x values. Output values are the y values, okay? So yeah, x values, y values. And we have a domain here. So all our x values, this coordinate is at -3, -2. So its x value is -3. And then it's not continuous data, so we just make a list. This x value is -1, 0. This x value is 1, 2. This x value is 3 up 4, so 3. So yeah, our domain is our x values, -3, -1, 1, and 3. And when you make a list like this, you can do the kind of bracket thing. Don't know what those are called actually, but yeah, that's what we learned in the video, is how you make a set. And then for our range, for our outputs, we're going to look at our y values. The outputs are our y values. So we've got -2, 0, 2, and 4. Okay, and that's how it's done. Now that's for when you have points, and it's also known as discrete data. We'll talk more about that in a couple lessons. But for this data, it's continuous, okay? It's continuous. Now what that means is, oh, excuse me, my goodness. All right, what that means is that we can't make a list because it counts everything in between. Partial amounts, halves, quarters. Everything's counted in between. And so we have 2 options. We either write our, so hold on just a second here. I'm gonna have to get the phone. Mr. Eichen speaking. Oh yeah, so do you happen to know the proper extension? Yeah, that's right. You accidentally dialed 215. So yep, if you call 214, it should get Miss Williams. All right. Oh, you know what? There's a button here. I've never done this, so we'll try it out, okay? Are you still there? Okay, so it didn't appear to transfer, so let me try that one more time if you don't mind. Okay, sorry. Yeah, let me try this one more time. Well, that was exciting. All right, so for continuous data, if you want to count everything in between, you're either going to have to use an inequality or something called interval notation. So the possible x values go from -1 to -2 all the way up to 3 for our x values. So you can either write an inequality like this. You can say -2, 3, and it's going to be all the x values in between and including 3 and -2. For interval notations, what you can do is you can write bracket -2, comma 3 for interval notations. So it's kind of different, but yeah. Notice they say the same things. This is saying you go from -2 to 3, and it counts everything in between. Go from -2 to 3, count everything in between. You don't have to do both. You can do one or the other. I notice most people seem to like the interval notation. This top one's called interval notation. All right, and then for the y values, you're going from -1 up to 2. So yeah, -1 up to 2, and then you put y in the middle, like so. And so that's how to write it as an inequality, but you can also do interval notation, bracket -1 to 2. The bracket means you can actually stand on it. If it happened to have been a circle, you would use a parentheses. It's kind of strange. Or if you have infinity, you would use a parentheses, but we'll get more into that tomorrow. But yeah, you can do one or the other. It doesn't matter which. Now we'll move on to identifying independent and dependent variables. Sometimes it's tricky to figure out which one's independent, which one's dependent. Notice it says that the independent variable represents the input values. The dependent variable depends on those input values. So you got to start there first before you can get those the dependent values. So typically, if a function's already written out, they've decided already what the inputs and outputs are. The x variable will represent the input, the independent variables, and the y values will represent the output or the dependent variables. So y depends on what x is. And notice this one represents the amount of y in fluid ounces of juice remaining in a bottle after you take x gulps. And they want us to identify the independent and dependent variables. So the independent variable is x gulps, x or number of gulps. That's the independent variable. You could take 3 gulps, you could take 4 gulps, 5 gulps. It's up to you. But then the oh, wait, I'm sorry, I got that confused. It's the independent variable. So, yeah, let's put that right there, independent variable. And then our dependent variable is going to be y, because it depends on the number of gulps. And y is the amount of juice left. Amount of juice left. Okay, so yep, our independent variable is the number of gulps. Our dependent variable is juice remaining or left. Okay. Well, moving right along, our domain here, oh, this is still talking about the same problem, so that's awesome. So yeah, your number of gulps could be 0, 1, 2, 3, or 4. So this is actually discrete data. You can't apparently have half a gulp, and that makes sense, I think. If you're doing half of a gulp, you might cough or something like that. So that could be dangerous. But notice it stops at 4, and there's going to be a reason for that. Okay, so let's find out what the output is. So they gave us the domain is 0 through 4. The range will be the ounces remaining. If you take 0 gulps, you're going to have 12 ounces remaining. If you take 1 gulp, you're going to have 9 remaining, 9 ounces remaining. If you take 2 gulps, you'll have 6 ounces remaining. If you take 3 gulps, it's getting lower. Yep, 3 ounces remaining. And finally, on that 4th gulp, after you take that 4th gulp, you're going to have 0 ounces remaining. It's going to be all gone, all gone. So, yep. It was a 12-ounce drink. That's where you start with. You got your 12-ounce drink. You haven't taken a gulp yet. Then you take a gulp, another gulp, another gulp, another gulp. By the 4th gulp, you've finished it off. And so our range is this right here. Our range is going to be the set of 12, 9, 6, 3, and 0. And that's it. Yep, that's our range. All right, the last thing is function notation. And function notation, I used to think was kind of silly when I was your age. I have more respect for it now. So it says, you know that a linear function can be written in the form y equals mx plus b. I don't know if you know that or not, but it can. So if you've got a linear function, it's going to have a slope, it's going to have a y-intercept, normally. But yeah, it says that you can also write the function using function notation. And what that does is it replaces y with f of x, or f parentheses x. It's not f times x. This is how you say this is f of x. And it says the notation f of x is another name for y. You read it as f of x. We'll look you there. All right, so if you're going to be, and this is where you see the value of function notation. If you're going to evaluate a function for many different inputs, what you do is you put the input in for x right there, and then you substitute it in elsewhere. And then you keep that function notation. So this says the function's value at 2 is, and then you can get your answer. So this would be -8 plus 7. So it's -1. And you write your answer like that. And what's awesome about it is it says, well, yeah, the answer is -1, but what was your input? It was 2. It's cool to have it written out that way rather than just y equals -1. And then we're also going to find the function's value at -2. And so we go -4 times -2 plus 7, and clean that up a little bit, you'll get 8 plus 7. So the function's value at -2 is 15. That's how it's done. All right. And then finally, our last example here, it says solving for the independent variable. And so on this one, it's a little bit tricky. It says find the value of x for which h of x equals -7. So notice it's not giving us x values. It's asking us to find the value of x. We're trying to find that when the function's value is -7. So what you do is you take that -7 and put it out front. it replaces h of x. So you go negative 7 equals 2/3 x minus 5. And then you add the 5 over and get negative 2. And then class, you could divide by 2/3, which you could, but I would recommend you multiply by the reciprocal instead on both sides. Multiplication property of equality, keep it balanced. And yeah, the 3's are gone, the 2's are gone. So you get x's, and then here you'll get negative 6. You'll get negative, whoa, I'm so silly. Not negative 6, the 2's went away. Negative 3. Negative 3 is what you'll get. And what it turns out is that the input of negative 3 would get you an output of negative 7. Okay, so it's kind of interesting. Well, that's what we got for function notation. Thanks for watching. Have a good day.